Now, finally, let's go to the double integrals.
Finally.
We're starting a new chapter, which is called multiple integrals. Super good. Double integrals are fun, and the beginning is very good. It's double the integral, but triple the fun. Yay! Yes. Not my idea, but I like it.
Wouldn't triple integral be triple?
Next.
Double integral be triple integral.
No, it's 12.1.
Wait,
This is 12.1.
Then what about 11.8? Are we just not
We don't do it. I don't know why.
Oh, so there's a web source that shows.
No, I need to delete it.
Oh, I had all the answers from before.
I know.
Oh.
Yeah, I already answered 11.8.
We're skipping 11.8. I don't know
My
why.
answers though.
So yeah, I took credit for it.
No. So, let's concentrate because we have only 15 minutes left. So, you remember 2D, the area below the graph was represented by this shape. We were also approximating it with the stupid triangles, rectangles, right? So, the area, the exact area without approximation was the integral from a to b, f of x dx. Well, guess what it's going to be in 3D? Make a guess. Intellectual guess. Double integral gives you what?
0.
If this is area, volume, this makes sense to have in 3D, right? So remember how we did finding volume with this using shell method and washer method? Screw that!
Oh yeah.
Well, that's the thing, like screw that. To be honest, nobody does that. And when, as a foreigner like me, as a TA, when I show up and I was teaching calculus 2 for the first time, I actually never seen any shell method and washer method before. I was like, why are they doing this? You could just take double integral. And then the Chinese international student was like, I don't know either. What is going on? And then the American student was like, yeah, this is how we do volumes. I'm like, no, nobody else does it like this. So you never do it again. Washer shell method only taught for engineers, I guess, to like have creativity of unfolding shells. I don't know. But we do double integrals. You want to find volume? The whole world is doing double integrals. And then some people do shell method. I don't know.
What I'm hearing is we're behind.
So, double integral will have this shape from C to D and A to B, f of x, y, dx, dy. See the interesting thing. Whoever is outside, in this case dy, then this should belong to dy from C to D. Whoever is next, x, then it should be A and B. So it should be what's the word? Correlated? Consistent, yeah. And then we're going to have dx, dy, dz, so it should be consistent. And that's how we know. So, a rectangle here, this is x, and this is x. No, this is x. X is from x1 and x2. So x is from A to B, and then y1 and then y2. So y is from C to D. And that's how you build a volume under the 3D shape, under the graph in 3D. And over the rectangle R. So it's not now a shadow like so in 2D. Now it's basically a shadow in 3D. So that's the idea. Makes sense. They say imagine you're slicing the cake, and that's exactly what you get. This 3D nice shape. The top of the cake will come from this 3D shape. Whatever that shape has, that's going to be the top of the cake. The bottom of the cake is the shadow in 2D. So that's a rectangle, as you can see. That's interesting. Here is nice visualization. You don't have to copy this. In 2D, it was the area under the graph. In 3D, it's a volume under the surface. Again, this 3D shape, this is a saddle, as you can see, comes from the shape. 2D is a rectangle. What kind of rectangle? This rectangle from A to B on x-axis and C to D on y-axis. So there is a rectangle here. Let's calculate. And the most important part is to teach you how to calculate all this. And that is interesting. You will see that it is pretty straightforward at the very beginning, at least. That's very good. You will enjoy it right now for like this 10 minutes of your double integral problem.
Only 10 minutes.
10 minutes of joy. Let's calculate the volume under the graph called 9 minus x squared minus y squared and over 0, 1, and 0, 2. Again, x and x is from 0, 1, and y is from 0 and 2. x1, x2, y1, y2. Or you can call it A, B, C, D. A, B, C, D. You are responsible now for building those integrals by yourself. Let's do it. This is nice visualization, but you need to build it. You see, I'm not going to do it for you anymore. So let's do it for the very first time. Volume is. Let's start with the x inside. So x goes inside. That means step away a little bit, have some space. X dx. It goes inside. X is varying from what to what?
0 to 1.
0 to 1, because this is what it says here. And on the pictures you can see from 0 to 1. That's my x. The function is in same 9 minus x squared minus y squared. This is the function, just like below the graph. We did in 2D. This is going to be below the 3D graph. The second integral will be dy. Then I'm putting here y is jumping from what to what?
0 to 2.
0 to 2. You can see it from here, 0 to 2, or from this notation. You finished building integral successfully. Now you need to learn how to actually find it. Let's see.
Wait.
It's the same thing, but I wanted to show you how you write it down from scratch. Here's what we wrote down. As you can see, people don't even put parentheses. So this is a very common idea. You show it in any country, people who know math, they know what it means. It means a volume below this surface above this square or rectangle. How to calculate it? At first, you will start with putting parentheses, and let's match the color blue with blue, like so. When I put parentheses like so, this inside integral is just integral with respect to x. And we know how to take partial derivatives, so we do know how to undo partial derivatives. We're going to integrating this integral with respect to x. This is my variable, and this is constant, whatever. Right? So now constants don't go to 0 though, because you're not differentiating, you are integrating them. So be careful. Leave the red color for now, don't touch it. Red color will become black, which means it's waiting its own turn. So dy is still there, we don't do it right now at this moment. We first do the x part. Integral of 9 with respect to x gives you?
Minus.
Good job. Integral of x squared,
X cubed over 3.
x cubed over 3. Integral of y squared, which is a constant with respect to x, is?
Negative times y.
Times x. Does it make sense? How cool is that? So I will put this in black. Y squared is a constant with respect to x. But then we finished integration. So something is missing here. What is that?
Bar.
The bar. That's how I teach it, right? The bar. We're going to put brackets. Some people don't put those brackets. If you put brackets, you don't have to put a bar. You can just put 0 and 1. This is where notation is not consistent between countries. Some people leave it like this. Some people want to make a reader less confused, so they write x equals 0 and x equals 1. This will help your brain to know that you're not plugging 1, 0 into y. You're plugging x into x. I was teaching in Calculus 1 how important this is. That's why you was taking points off when you don't write down dy dx. This now is important. We plug 0 and 1 into x's, not y's, z's, t, m's, and g's. Equals. We did not finish calculating this integral, so the outside integral is keep waiting. Open the parentheses. Plug 1. Remember how we do it. Plug the top minus plug the bottom. X into x. So 9 times 1 minus 1 cube over 3 minus y squared times 1. Make one parenthesis minus 0, and let me just keep 0, 0, 0 gives you 0. Okay, so that fits the space now. With time you do it faster, so you don't have to make so many steps to calculate something so algebraic. You should be good with algebra, okay? 9 minus 1/3 minus y squared dy. This is the integral you could do in Calculus 1 class. If you give this integral in Calculus 1 right now, they will be able to do it. So we decrease the dimension. We used to have three-dimensional object with two integrals. Now we have one integral which is two-dimensional object. We decrease the dimension, and that is important concept in general. You add the dimensions or you get back to less dimensions if you want to. And now you know what to do. With respect to y, 9 becomes 9y. Well, I actually could just add up those two numbers, right? Yeah, that would be smarter. So you will have 26/3, yeah? 26/3y minus y cubed over 3. A bar, you don't even have to put brackets. Or if you want, you can put brackets. Let's stay consistent, so put a bar from 0 to 2. Now, you don't have to write down y equals 0 and y equals 2 because it's only one-dimensional integral. There's no other variables going on. So you see, that's why I'm not doing that. Plugging in the top minus the bottom gives me 52/3 minus 8/3, which is 44/3. Remember, the volume should be positive. If you get a negative volume, you messed up. Right? Notice how we turned the double integral with x and y into a single variable integral with y only. This idea will be extremely important when we're going to get to triple integrals.
Triple.
We'll get there one day, not today.
Do you want to do one more or go?
Wouldn't you want to go like this? What about
Questions? Wait. Questions? Yeah. Good question. I will answer it right now. Don't go yet. Does it matter which one do we do first? On Wednesday, we're going to find out that we could do it this way, and the answer will match. Yes, the question?
When we only solved one integral, was that the area under along F?
That's a good question. So, let me say it like this.